Guglielmo Marconi's first radio transmissions in 1894 have spread into space for over 100 years at the speed of light. They passed Sirius in 1903, Vega in 1919, and Regulus in 1971. That signal has already passed over 1,000 stars. Anyone orbiting one of those stars with a really good receiver could detect Marconi's signal and know that we are here. Radio waves are the longest and contain the least energy of any electromagnetic wave. While visible light is measured in minute fractions of an inch, radio waves vary from about 19 centimeters, about the length of a water bottle, to waves the length of cars, ships, mountains, all the way up to monstrous waves longer than the diameter of our planet. Heinrich Hertz discovered radio waves in 1888. The first commercial radio station went on the air in Pittsburgh, Pennsylvania on November 2, 1920. Then, in 1932, a major discovery by Carl Jansky at Bell Labs revealed the stars and other objects in space radiated radio waves. Radio astronomy was born. However, scientists need giant antennas to detect weak, long-wavelength radio waves from space. The enormous Arecibo radio dish antenna measures 305 meters in diameter, over 3 football fields. Scientists can link the signals from an array of separate radio antennas to focus on tiny slices of distant space. Such arrays act as a single immense collector. This giant New Mexico array uses 27 parabolic dish antennas shaped into a giant Y, with each arm capable of stretching for 13 miles. Scientists have even spread these linked antennas across the globe. One of the largest stretches from Hawaii to the Virgin Islands and acts like such a powerful telephoto lens that a baseball sitting on the moon would fill its entire field of view. Many of the greatest astronomical discoveries have been made using radio waves. Pulsars, the existence of giant clouds of superheated plasma, which are among the largest objects in the universe, and even quasars, such as this one over 10 billion light-years away, were all discovered using radio waves. Radio waves also provide more local information. Astronomical objects that have a magnetic field usually produce radio waves, such as our Sun. Thus, NASA's STEREO satellite is able to monitor bursts of radio waves from the Sun's corona. Wave sensors on the WIND spacecraft record the radio waves emitted by a planet's ionosphere, such as the bursts from Jupiter, whose wavelength measures about 15 meters. Radio waves fill the space around us to bring entertainment, communications, and key scientific information. We can't hear these radio waves. When you tune your radio to your favorite station, the radio receives these electromagnetic radio waves and then vibrates a speaker to create the sound waves we hear. We may not be able to tap our toes to the cosmic radio transmissions, but we certainly discovered much about our universe's grand cosmic dance by listening to them. Microwaves can pop your popcorn. They can catch you speeding. They carry thousands of phone channels to speed your calls. But can microwaves help us learn about our world and our universe? Let's find out. With wavelengths ranging from 30 centimeters down to 1 millimeter, microwaves fall between radio waves and infrared. Microwaves are used in Doppler radar, which is widely used for short-term localized weather forecasting and what you see on TV weather news. Satellites have revolutionized weather forecasting by providing a global view of weather patterns and surface temperatures. This unique perspective has greatly increased the accuracy of tropical storm and climate forecasts. Different wavelengths of microwaves, grouped into bands, provide different information to scientists. Medium-length, C-band microwaves penetrate through clouds, dust, smoke, snow, and rain to reveal the Earth's surface. Satellite microwave measurements reveal the full Arctic sea ice cover every day, even where clouds exist. These measurements show great variability from year to year, but also an overall decrease in Arctic sea ice since the late 1970s, illustrated here with maps and a time series of Arctic sea ice in September at the end of the summer melt. The Japanese Earth Resources satellite uses longer wavelength L-band microwaves for forest mapping by measuring surface soil moisture, such as this image of the Amazon basin, to identify areas of recent deforestation. L-band microwaves are also used by global positioning systems, such as the one in your car. Scientists routinely combine microwave information with information from other parts of the EM spectrum to study the composition of cosmic dust or of a supernova, such as this supernova image that combines X-ray, radio, and microwave data. This recently known supernova in the Milky Way exploded just over 140 years ago at the time of the American Civil War. One important phenomenon is unique to microwaves. In 1965, using long L-band microwaves, Arno Penzias and Robert Wilson made an incredible accidental discovery. They detected what they thought was noise from their instrument, but was actually a constant background signal coming from everywhere in space. This radiation is called cosmic microwave background, and if our eyes could see microwaves, the entire sky would glow with a nearly uniform brightness in every direction. The existence of this background radiation has served as important evidence supporting the Big Bang theory for how our universe began. Microwaves have become both staples and wonders of modern life. They are also the backbone of communications and of Earth sensing systems, and they are an excellent guide to the ancient history and origins of our universe.
Humanity has always been drawn to the night sky. We draw pictures in the stars, track the planets, see signs and portents in celestial objects. But so much of the universe is beyond our reach. Vast distances separate us from the sights that might answer some of our biggest questions. How do galaxies form? How do stars and planets come to be? Do distant planets have the conditions necessary for life? To construct and test our theories, we need to see what's happening. So we build tools to extend our vision. They get bigger, more powerful, more advanced. As time goes on, astronomy stops relying on the light we can see only with our eyes. When you look at the world, you're seeing something we call visible light. But visible light is really only a certain form of radiation. Our universe is full of many different types of radiation. It surrounds us. Our bodies evolved to detect visible light with our eyes, but they also evolved to detect another kind of radiation called infrared light. Our bodies feel infrared light as heat. This infrared radiation was discovered by the astronomer Frederick William Herschel. Herschel knew that a prism could be used to break white light into colors. He wanted to know whether the colors had different temperatures. They did. But then Herschel measured the empty space just beyond the red light. Though no sunlight was visible, it was hot. Herschel had just discovered invisible infrared radiation. Humanity now knew that there were forms of radiation that could not be seen. They could be anywhere, all around us. How many were there? What were they up to? What were they hiding? Obviously, we had to find out. A type of energy that travels through the universe in the form of waves is called electromagnetic radiation. The entire range of it, from high-energy gamma rays to low-energy radio waves, is called the electromagnetic spectrum. Although our eyes can see only visible light, we can build tools like infrared detecting cameras to see other forms of radiation. These tools are man-made eyes that view invisible radiation for us and transform it into pictures. Objects can emit all kinds of radiation. Observing the entirety of that radiation gives us a true picture of an object. When we turn these tools on space, they open up the entire cosmos to us in its full glory. When we look at the night sky, we see stars and planets, galaxies and nebulae in the form of visible light. But if we could see in infrared light, the sky would appear very different. For one thing, infrared light's long wavelengths penetrate clouds of gas and dust. The shorter wavelengths of visible light are stopped and scattered as they fight through collections of particles. So by detecting infrared light, we can see through clouds of gas and dust to warm objects inside, like just forming stars. Objects that don't glow with any visible light of their own, like planets, are still often warm enough to radiate infrared light, perhaps allowing us to glimpse them. And by observing how infrared light from a planet's star passes through its atmosphere, we acquire clues about the planet's composition. The dust left behind by distant planets as they form will also glow in infrared, helping to show us how planets are born. So infrared helps us see objects like these in our own galactic backyard, but it can also help us observe the first objects that formed in the universe after the Big Bang. Imagine you gave a letter to the post office in a galaxy billions of light years away and addressed it to Earth. It would travel for an incredibly long time. When it finally arrived at its destination, the person who opened it would be getting news from billions of years earlier. The light from the first stars to shine in the universe is something like that. It left the stars ages ago and is still out there in space, traveling the vast distances between galaxies. If we could see it, we could see those galaxies as they were in the early universe. Essentially, we would be seeing back in time. But we haven't been able to see it. Why? Because the universe is expanding. As light travels across space, it's stretched like taffy by the expansion. The first stars gave off mostly visible and ultraviolet light, but the stretching changes those waves into infrared light. This is called redshifting. The only way to see that light as it arrives in our region of the universe is to look for that faint infrared glow. By capturing it, we will be able to create images of the first galaxies to form in the universe. By witnessing the birth of the first stars and galaxies, we deepen our knowledge of how the universe as we know it came to be. How did we get from those first blazing stars to the islands of billions of stars we see today? What will we learn about how galaxies grow and evolve? How did the chaos of the early universe transform into order and structure? NASA is currently building the James Webb Space Telescope. With its huge infrared capturing mirror and distant orbit far beyond the moon, Webb will allow us to view the cosmos as we've never seen it before. Webb will search for signs of water vapor on planets around other stars. It will take pictures of the universe's infancy. Webb will reveal the hidden stars and solar systems forming within cocoons of dust. The answers to some of the universe's biggest mysteries and more questions we haven't thought to ask are waiting out there for us in the form of infrared radiation. All we have to do is look.
Swirling spiral arms of galaxy M33 can be seen in visible light, but the true extent of these spiral arms are revealed in ultraviolet light. Just as a dog can hear a whistle just outside the range of human hearing, bugs can see light just outside the range our eyes can see. A bug zapper emits this ultraviolet light to attract insects. Johann Ritter conducted an experiment in 1801 to find out what, if any, electromagnetic waves are beyond violet. Ritter knew that photographic paper would turn black more rapidly in blue light than in red light, so he tried exposing the paper beyond the violet end of the visible spectrum. Sure enough, the paper turned black, proving the existence of light beyond violet, ultraviolet rays. These ultraviolet rays, or UV radiation, vary in wavelength from 400 nanometers to 10 nanometers and can be subdivided into three regions: UVA, UVB, and UVC. Visible light from the sun passes through the atmosphere and reaches the Earth's surface. UVA, long-wave ultraviolet is the closest to visible light. Most UVA also reaches the surface, but shorter wavelengths, called UVB, are the harmful rays that cause sunburn. Fortunately, about 95% of these harmful UVB rays are absorbed by ozone in the Earth's atmosphere. UVC rays are the shortest and most harmful and are almost completely absorbed by our atmosphere. The ozone monitoring instrument aboard NASA's Aura satellite detects ultraviolet radiation to help scientists study and monitor the chemistry of our atmosphere, including UV-absorbing ozone. While atmospheric protection from harmful UV radiation is good for humans, it complicates the study of naturally produced UV rays in the universe by scientists here on the Earth's surface. Young hot stars shine most of their light beyond the visible light spectrum at ultraviolet wavelengths. Scientists need telescopes in orbit above the Earth's UV-absorbing atmosphere to find and study these UV-bright regions of star formations in distant galaxies. New young stars in the spiral arms of galaxy M81 can be seen in this Galaxy Evolution Explorer GALEX image from NASA. Chemical substances, both atoms and molecules, interact with UV light, making this region particularly interesting to scientists. An ultraviolet instrument aboard Cassini has detected hydrogen, oxygen, water ice, and methane in the Saturn system. UV data have also revealed details of Saturn's aurorae. Scientists also use UV waves shining from distant stars to view permanently shadowed regions of lunar craters. The Lyman Alpha Mapping Project, or LAMP, instrument aboard NASA's Lunar Reconnaissance Orbiter can use this faint starshine to look for possible water ice on the Moon. Ultraviolet rays may be harmful to humans, but they are essential to studying the health of our planet's protective atmosphere and give us valuable clues to the formation and composition of distant celestial objects. A star explodes in a blinding supernova, spraying X-rays across the galaxy to tell its tale. X-rays also tell a dentist which tooth to drill and a surgeon which bones to mend. In 1895, Wilhelm Röntgen discovered that firing streams of X-rays through arms and hands created eerie, but detailed, images of the bones inside. X-rays are high-energy light rays with wavelengths between 3 and 0.03 nanometers, so small that some X-rays are no bigger than many individual atoms. In laboratories, scientists fire beams of X-rays at unknown substances to learn what elements they contain and to decode their atomic structure. This is how scientists unraveled complex molecules like penicillin and DNA. Scientists can also detect the X-rays emitted from extremely hot and energetic objects in the universe. NASA's robotic rovers recorded X-rays to identify the spectral signatures of elements such as zinc and nickel in Martian rocks. X-rays can also reveal an object's temperature, since temperature determines the wavelength of its radiation. The hotter the object, the shorter that wavelength is. X-rays come from objects that seethe at millions of degrees, such as pulsars, black holes, supernovas, or the plasma in our sun's corona. Our sun has a surface temperature of around 6,000 degrees Celsius and radiates most of its energy in visible wavelengths. But it is easier to study the massive energy flows in the corona's energetic plasma by observing X-rays, like this image from the Hinode satellite, a joint Japanese-NASA mission. NASA's SOHO satellite produced these X-ray images of the sun that allow scientists to see and record these energy flows within the corona. NASA's orbiting Chandra X-ray Observatory detects X-rays created by objects spread far across space, such as this supernova explosion that occurred 10,000 light-years from Earth. The colors in the gas and dust cloud correspond to different energy levels of the X-rays created by the blast. X-rays at different wavelengths provide information about an object's composition, temperature, density, or its magnetic field. Human eyes may not be able to see X-rays, but from seething cosmic bodies to individual atomic elements, X-rays provide a wealth of information to exploring scientists. Created by the hottest, most violent, and most energetic objects and events in the universe, gamma rays travel across vast stretches of space, only to be absorbed by Earth's atmosphere. Scientists had no way to detect and study gamma rays from the cosmos until high-altitude balloons and rockets carried gamma ray sensors above the atmosphere. Deadly to humans, gamma rays are created on Earth by natural radioactive decay, by nuclear explosions, and even by the lightning and thunderstorms. Coronal mass ejections from our sun emit gamma rays, followed by masses of charged particles. Monitoring these gamma rays provides scientists with an early warning of incoming charged particles that may cause disruptions in power and communication networks. The most energetic of all EM waves, gamma rays carry enough energy to kill living cells. Doctors are able to selectively use gamma radiation to destroy cancer growths. Gamma ray wavelengths are the shortest of all electromagnetic waves, about the size of an atom's nucleus. In fact, it is so short that the rays sail through atoms as easily as comets sail through our solar system. This makes detecting gamma rays difficult for scientists. Gamma ray detectors typically contain densely packed crystal blocks. As gamma rays pass through, they collide with electrons in the crystal. The sensor doesn't directly detect gamma rays. Rather, it detects the charged particles created by those collisions. Scientists have used gamma rays to determine the elements that make up Martian surface soils. When struck by cosmic rays, chemical elements in soils and rocks emit uniquely identifiable signatures of energy in the form of gamma rays. The Gamma Ray Spectrometer on NASA's Mars Odyssey orbiter detects and maps these signatures, such as this map of hydrogen concentrations. Gamma rays stream from stars, supernovas, black holes, and pulsars to wash our sky with gamma ray light. NASA's Fermi Gamma Ray Space Telescope imaged the location of these sources, mapping out the Milky Way galaxy by creating a full 360-degree view of the galaxy from our perspective here on Earth. While the visible light sky is predictable and follows regular patterns, the gamma ray sky does not. Bursts of high-energy gamma radiation arrive from deep space every day. These explosions of gamma rays last fractions of a second to minutes, popping like cosmic flashbulbs, momentarily dominating the gamma ray sky and then fading. This video of the Vela pulsar beams gamma rays every 89 seconds as it rotates. Gamma ray bursts are the most energetic and luminous electromagnetic events since the Big Bang and can release more energy in 10 seconds than our sun will emit in its entire 10 billion year expected lifetime. NASA's SWIFT satellite recorded this gamma ray burst of an exploding star 13 billion light-years away. It is among the most distant objects ever detected when the universe was just 630 million years old. A recent observation of a gamma ray burst produced the greatest total energy to date, equivalent to 9,000 typical supernovae. By continuing to study gamma rays, we will unlock important new understanding in astronomy, its use in medical treatments, and allow us to further enhance our protection for our satellites and other electronics here on Earth.